Welcome to Lecture 3, First Order Ordinary Differential Equations. Standard form of a first order differential equation in the unknown function y of x is y prime, which is also written as dy over dx equals to f of x of y. Differential form of a first order differential equation is of the form m of x of y dx plus n of x of y dy equals to 0. Types of first order ordinary differential equations. Number 1, separable equations. A separable equation is an equation that can be put in the form g of y dy equals to f of x dx. Example 1. Suppose we have dy over dx equals to 2x squared over y cubed. How do we solve this equation? Well, let's first cross multiply. So we have y cubed dy equals to 2x squared dx. Now, if you look carefully, this equation, we have been able to separate y from x. Therefore, it satisfies this condition here. Now, we need to integrate both sides. So we have y cubed dy, 2x squared dx, plus, of course, the constant of integration. Remember from techniques of integration, when we integrate y to n, we simply add 1 to n, then divide by n plus 1. Therefore, we have y divided by 4 equals to 2x cubed divided by 3 plus the constant of integration. This is the required general solution. Example 2. Suppose we have dy over dx equals to xy squared plus x, yx squared plus y. Now, let's first cross multiply. We can now factor out y in brackets x squared plus 1 dy. We can also factor out x, y squared plus 1 dx. We can divide both sides by x squared plus 1 and simultaneously by y squared plus 1. This will cancel, remain with y over y squared plus 1 dy. This and this will cancel, we remain with x over x squared plus 1 dx. Now, since we have been able to separate y variable from the x variable, we can now integrate both sides to get the required solution. Plus constant of integration. For us to be able to integrate this equation, we need to use the technique of u substitution. Let u be equal to y squared plus 1, du dy will be equal to 2y. Therefore, dy is 2y. Therefore, dy is equal to du over 2y. On this other side, let v be equal to x squared plus 1. dv over dx will be equal to 2x. Therefore, dx is equal to dv over 2x. Now, we can make this substitution in our equation. So we have y u du over 2y equals to x v dv over 2x plus, of course, the constant of integration. Y and y will cancel. We can pull out a half. The integral of 1 over u du equals to x and x will cancel. We can pull out a half. Integral of 1 over v dv plus the constant of integration. So this will be a half. The integral of 1 over u is ln u equals to a half. The integral of 1 over v is ln v plus, of course, the constant of integration. But u is equal to y squared plus 1 and v equals to x squared plus 1. Therefore, we need to substitute u and v. We have a half ln y squared plus 1 equals to a half ln x squared plus 1 plus the constant of integration. Now, we can multiply all through by 2. So we have ln y squared plus 1 equals to ln x squared plus 1 plus 2c. Now, c is a constant. Constant times 2 will give us another constant. So the resultant constant, let it be a. So we have ln y squared plus 1 ln x squared plus 1 plus a. Now, let's raise both sides to exponential. So, exponential ln y squared plus 1 exponential ln x squared plus 1. Of course, plus the constant. Using the laws of indices, this part can be splitted into 2. So we have ln y squared plus 1 equals to exponential ln x squared plus 1 times exponential to the a. Now, because we have exponential and ln at the same time, these two will cancel, giving us y squared plus 1. Again, exponential and ln will cancel, giving us x squared plus 1. Exponential to the a is a constant, so let's call it a. This is the required general solution. Example 3. Suppose we have exponential to the x dx minus y dy equals to 0. Now, in this equation, the x and y variables have already been separated, so we just need to integrate. Therefore, we have the integral of exponential to the x dx minus the integral of y dy equals to the constant of integration. Now, when we integrate exponential to the x, we simply get exponential to the x minus, when we integrate y, we get y squared over 2 equals to c. This is the required general solution. However, in this question, we had been given an initial condition of y0 equals to 1. Remember, 0 represents the x value and 1 represents the y value. Therefore, we can make the substitution. It becomes exponential to the 0 minus 1 over 2 equals to c. Therefore, exponential to the 0 is 1 minus a half equals to the c. Therefore, the value of c is a half. Now we can substitute c with a half. So we have exponential to the x minus y squared over 2 equals to a half. This is the required particular solution or unique solution. Example 4. Suppose we have dy over dx equals to x squared plus 2 over y. How do we solve this? Well, let's first cross multiply. So we have y dy equals to x squared plus 2 dx. Now, since we have separated the variable, we can integrate. So the integral of y dy equals to the integral of x squared plus 2 dx. Correct. The integral of y is y squared over 2 equals to the integral of x squared is x cubed over 3 plus the integral of 2 is 2x plus, of course, the constant of integration. And this is the required general solution. Example 5. Suppose we have dy over dx equals to y squared x cubed. How do we solve this? First of all, let's multiply both sides by dx. We have dy equals to y squared x cubed dx. Now let's divide both sides by y squared. So we have 1 over y squared dy equals to x cubed dx. Since we have separated the variable, we can now integrate both sides. Integral of 1 over y squared dy equals to integral of x cubed dx plus constant of integration. 1 over y squared can be written as y to the minus 2 dy equals to integral of x cubed dx plus c. Now we need to add 1 to minus 2, that will give us minus 1, then divide by minus 1, which will simply be minus, equal to x to 4 over 4 plus c. This can be written as minus 1 over y equals to x to the 4 over 4 plus c. We can take this one this side, so we have 1 over y plus x to the 4 over 4 equals to the constant c. And this is the required general solution. Example 6. Solve x dx minus y squared dy equals to 0. Now in this equation, the variables are already separated. Therefore, we need to integrate x dx minus y squared dy equals to the constant of integration. So we have x squared divided by 2 minus y cubed over 3 equals to c. And this is the required general solution.